Welcome to Science Saturday. Today we are going to learn about electricity. The word electricity sounds a lot like a very small particle that you might have heard of. That particle is called an electron. If you look at atoms, the smallest pieces of elements that still have the properties of whatever element they are made of subatomic particles, things like protons and neutrons and electrons. The word electron comes from the word for electricity because when they were first discovered, scientists realized that this was the vehicle that carried electricity, that this was electricity. Electricity is a flow of electrons, and these particles are very small, they are negatively charged, and today we're going to learn what materials conduct electricity and what materials do not. And we're going to do it with the help of a plasma ball. Before I turn off the lights, let me tell you how this works because this device is really cool. Plasma balls have in the center a Tesla coil. That's what this rod coming up in the center is. The Tesla coil was invented by Nikola Tesla many years ago, and it does something really cool. It takes a current and it alternates it back and forth really at high speeds. Basically what it's going to do is send excited electrons out in every direction. And those excited electrons, when they pass through the gas in the sphere, they will cause it to glow. If there was a hole in this plasma ball or a crack in the sphere and the gas that was inside here was the same as the gas that I'm breathing, oxygen and nitrogen, then when we turned on the plasma ball, we would not see anything at all. But because this sphere is full of neon and argon gas, when we turn on the plasma ball, we will see beautiful colors, bright pinks and purples. Give me a sec to turn off the lights and then I'll show you what it looks like. All right, now that I have the lights dimmed a bit, we should be able to see this just a little bit better. And there we go, it's on. Beautiful, absolutely beautiful colors. And you can see that right now, the electricity flow is not going in any particular direction. It has a very random, scattered flow of going in every direction out from that center point. And if we place materials on here, we can test out different materials and see which things conduct electricity and which things don't. Because if I put something that conducts electricity on top of this plasma ball, then we will see the current. We will see all of these excited electrons that we can visualize because they're making this gas glow. We will see them all go up toward the conductor. If we put something on here and we really don't see a change, the flow of electrons remains about the same, then we'll know that that substance is an insulator. It does not conduct electrons. So the first one that we're going to try is rubber. I have a rubber eraser here, and if I place another one on top, we really don't see a big change. It looks about how it did before. So rubber is an insulator. Next we will try plastic. If I put plastic on top here, we don't see a big change. Plastic is also an insulator. Dry wood, I've got two popsicle sticks here. Dry wood is an insulator. Now we're going to try metal coins. So I put a quarter here and then another one here. And we do see a big change. Now most of the current is coming up through our metal coins. Metal is a conductor, and it's a very good conductor of electricity. That's why when you look inside wires with all our electronic devices, you will see metal, usually in the form of copper, metal wires that are wrapped in layers of rubber and plastic to insulate that electric current and keep it flowing where we want it to go. Now, I told you, metal is an excellent conductor of electricity, and it is, but metal is not as good a conductor as I am. It doesn't matter if it's my hand, or two fingers, or my face, whatever part of me touches the plasma ball, all of the current is drawn right toward that spot, almost all of it. And you can see that I am a very good conductor of electricity. And my question for you is why? Why am I such a good conductor of electricity? I'd like you to pause the video for just a sec and discuss it if you have someone that you're watching the video with. See if you can come up with some ideas for why I conduct electricity. In school visits, most often when I ask this question, kids will come up with fantastic connections. they will say things like, you have iron in your body, and iron is a metal, and we know that metal conducts electricity, so maybe that's why we conduct electricity. And you're right, there is iron in my blood, but the amounts are very small, and they don't really contribute to me being able to carry and conduct an electrical charge. Another connection that kids will often remember or realize is that our heart and our nervous system have small electrical impulses. That's how your heart keeps beat. And there are small electrochemical charges that are happening all the time with our nerve cells to make our nervous system work. And that is true too, but that is not why I conduct electricity. There's something else I have inside me, and I have a lot of it inside me, and it's water. Water conducts electricity really well. You can see this water bottle, even though it is encased in a layer of plastic, it is conducting a current quite well, even better than our quarters did. Water is a super good conductor of electricity, and that's why we need to be very careful not to let water and electricity mix. If you're swimming in a swimming pool and there's lightning, what do you have to do? Get out of the pool. And the outlets that we have in bathrooms and kitchens need to have that special safety feature so that if too much current comes out, they shut off. Because if you have an electric device, something that's powered by electricity like a toaster or a hairdryer, and it falls into a sink that has water in it, that could result in electrocution. That can draw out so much current so fast it could be really dangerous. So what conducts electricity? Water, you and me, metal, and what things are insulators that do not conduct electricity? Rubber, plastic, wood, glass, and a few other things. Before I turn off the plasma ball, I want to show you just a couple other things about electricity. The first is that it can jump from one place to another if enough charge builds up. We see this in the real world with lightning on a very big scale, but we can also see it here on the plasma ball. We can make a tiny little miniature bolt of lightning if we put a quarter on the top, a metal coin, and then we bring another metal coin and just hover it right above. Because right now, there are electrons, excited electrons, collecting on the coin. And our coin is a conductor. It doesn't want to hold on to extra electrons. It wants to pass electrons to something else. It wants to conduct them. So if I bring another coin close, the electricity will jump. That little bolt of lightning is only a few millimeters tall, but it is genuine lightning. Now, quick safety tip. If you are doing this at home, if I put a coin on here and I am touching my finger to the coin firmly, then, whoops, I don't feel any type of pain. It just feels like the coin is a little bit warm. But because I am a conductor, if I bring my finger close to the coin but don't quite touch it, if I hover right above it, then I will get shocked by that miniature bolt of lightning just like the coin did. Ugh. And it doesn't feel good. It's like getting pinched. It is a little bit painful, and it leaves just a superficial burn on the skin of your finger, which will wear off after a few hours. So if you have a coin and you're experimenting with making some little bolts of purple lightning in your classroom or at home, make sure that you touch it with assertiveness and confidence, because if you pick it up like this, you don't get zapped at all. But if you're like, ooh, is it gonna get me? Is it gonna get me? Then it will, and you will get zapped by the little bit of lightning. The next thing I want to teach you about electricity is that it is invisible. Almost always, we don't see excited electrons. The excited electrons that are being created by this Tesla coil in the center of the plasma ball, they are radiating out in all directions, and they don't stop when they get to this plastic layer. They extend beyond, but the amounts that there are very small, and I can't sense them with my physical senses. I can't see them, I can't feel them. The only way I can prove to you that they are there is by bringing a light bulb close. The light bulb is lighting up because the excited electrons are passing through the coil, which has a gas that glows white when electrons run through it. Typically, when you plug in a light bulb, the electrons come in through the bottom and light up the light bulb this way. But with our plasma ball, we can light the light bulb up even better just by bringing the coil close. Now, this does not work with an incandescent light bulb. This is a fluorescent light bulb, and it works because the gas that is inside here, the mercury gas, glows white when electrons go through it, and it does not take very many electrons. It does not take very much energy to light up this light bulb. But this is an incandescent light bulb, and its mechanism is very different. This light bulb has a small wire called a filament on the inside, And when electricity runs through that wire, it heats it up so hot that the wire glows, and that's what gives the light. It takes much more energy to do that. And so this light bulb, no matter how I try to set it up on a plasma ball, there's no way I'm going to get this light bulb to light up because it takes much more energy to get this light bulb to light than it does the fluorescent light bulb. Last thing, before we turn off the plasma ball, I want to show you a cool setting that it has. This is the off position, and when I turn that plasma ball off, what I'm doing is disconnecting wires. There's a continuous length of wire that goes from the cord in the plasma ball into the plug that's plugged into an outlet. That's where it gets its power. And if I push the switch all the way forward, they're disconnected. If I turn it that way, then they are connected, and the current of electricity is flowing all the way in. But if I turn it one step farther, now instead of being disconnected or connected, they are just barely separated so that slight vibrations will cause them to touch and turn the plasma ball on. So if I tap it, I can get it to turn on. And guess what? Sound is a vibration, and so if I clap, I should be able to turn on the plasma ball just by the noise that I'm making. A lot of fun. The plasma ball has been a great source of information for us to experiment and learn about currents of electricity, and now we're going to turn on the lights and talk about static electricity. We're going to be using our materials that are insulators to gather extra electrons, because if you have excess electrons by a conductor, the conductor just passes them on to the next thing. But if you have excess electrons by something like a rubber balloon, that rubber balloon will develop a static charge. I am wearing gloves because I worked as a molecular biologist for several years in a lab where I wore latex gloves every day. And all of that exposure to latex gave me a little bit of an allergy. I will get a rash if I touch this balloon with my bare hands. But if you're doing this at home, the mittens are completely optional. I have asked an assistant to come in and help with our first little experiment or demonstration. Now I am going to take this balloon and I'm going to rub it on your hair.
My luscious locks.
Your luscious locks. Your hair is made out of protein, and that protein is made out of molecules that have atoms in them. Do they have electrons?
Yeah.
They do, and
Obviously.
this balloon has electrons too. And there's going to be a transfer of electrons. Electrons from your hair are going to go onto the balloon. That's going to give the balloon a negative
Static.
charge. Yes, static electricity, exactly. And then, since the balloon has a negative charge and your hair lost electrons, your hair is going to have a bit of a positive charge, and they will be attracted to each other. Really cool, right? If we get enough of a charge on this balloon, it will stick to the wall. Watch this. And it's staying on the wall.
Hi.
Should we have a
How you
little
doing?
contest? Here, you stand right there. I'll see if I can blow it to you. And then you see if you can blow it back to me. Ready? Okay. Now, let's
It's
leave it there.
staying.
It is staying. Let's leave it there, okay? Give me 5. Thank you so much. Now, it's not just balloons that can develop static electricity, plastic can as well. This plastic PVC pipe that I got from the irrigation section of a hardware store can develop a static charge too. If I put a metal can here and then I charge up this pipe by rubbing it with a fuzzy cloth, when I get it close to the can will be attracted to the pipe. If the can is upright, there is too much friction for the can to move usually, and you'll just hear that little click of the static being transferred when it gets close to the can. But if I lay the can on the side, let me scoot back just a little farther so you can see that better. If I lay the can on the side, then when I bring the pipe next to it, there is much less friction and I can get it to roll. Now with a metal can, the can is attracted to the pipe, but if we use something that is made of plastic, so we have insulator and insulator, then if we charge them both, they will both have a negative charge and they will repel each other. So this is tinsel that I have tied so there is a knot at the top and not at the bottom, and you can see that this pipe still has a little bit of static, so if I put it close to the tinsel will stick to it. What I want, though, is for there to be so much static that excess electrons jump onto the tinsel, and then the tinsel will be repelled from the pipe. Like so. Oh, and then it sticks to the wall. This is a ton of fun, levitating orb. The reason why the tinsel spreads out is because once the tinsel is charged, every single strand wants to be as far away from the others as possible. And if instead of an orb, we have tinsel that is tied at the top, but then the strands are just free floating, then it ends up looking kind of like a starfish because the strands spread out in all directions. I've got to charge it again because you need to charge it in between each time that you do it. And then we'll give it a try. It's a little trickier to keep this one in the air, but as long as I don't get too close to anything, and as long as I can keep my pipe underneath it, it will stay floating. Though this is a lot of fun that you can do with static electricity, but a couple quick tips. It must not be too humid. If it's too humid and you have a lot of water in the air, then those water molecules, because they are such good conductors of electricity, they sort of grab off those extra electrons and you're not able to develop as good of a static charge. You might be wondering how long the balloon is going to stay on the wall, and it all depends. It depends on how much charge, static charge, the balloon had to begin with. It depends on what material the wall is made of. If you have something like a whiteboard or something that has some metal in it, they usually work pretty well for sticking the balloon. But a cinder block wall, like dry cinder blocks, those typically do not work for sticking a balloon. It depends on what material it is. You have to have something that has some sort of positive charge or materials that have some conductivity in it so that then there can be that attraction for the static charge to keep the balloon there. And how long it will stay depends on the weather as well. When the weather is humid, it's not going to stay as long. When the weather is really hot, it won't stay as long. So your best bet for these activities are in dry weather in the winter time when it's cooler. That's when the static electricity activities work the very best. Based on the little experimenting and playing that we've done in the last day or two here, my prediction would be that this balloon would stay on the wall for about 3 or 4 hours before it would finally drop. It's stuck on there pretty well. I hope you enjoyed this episode of Science Saturday, and let's review just a couple of the things that we learned. We learned that electricity is the flow of electrons, super small subatomic particles that are on all atoms. Electrons are fascinating particles, and we could spend a whole entire Saturday talking just about electrons and some of the amazing things that we've discovered about them. But in today's lecture, we just focused on which materials conduct electricity, which materials don't, and then some fun and really interesting things you can do with static electricity. Work hard, grow smart, and I will see you next week. We want to give a special thank you to our patrons on Patreon. We don't run any ads on these Science Saturday videos, and they are supported 100% from our members on Patreon. If you would like to join, remember there are bonus worksheets and things that you get to go along with every single Science Saturday lesson. And now, we're going to sing a safety song while we highlight the members who are Elements and Champion patrons. You ready?
Ready.
Protect both your eyes, you only have two. Safety goggles on, that's the right thing to do. Be safe doing science at home. Lab coat and gloves cover the skin. Keeping you safe is what we call win-win. Be smart doing science at home.
Consider risk and danger, evaluate the cost. Be aware of circumstance to minimize the loss.
Oh, if you make a mess, clean it up quick. That's common sense and a real good life tip. Be good doing science at home. We hope that you learn lots of things here. Join us each week for science and cheer. Be smart doing science at home. Aww. There goes another fire truck. We'll just wait for them to pass.
I know why you couldn't do it on Dad.
Yes, Dad doesn't have any hair. So we're going to do it on you. All right.
Sorry, Dad.